All right, pre-calc students, welcome to lesson 3, properties of logarithms and solving log equations. Okay, so what we're going to do is just head straight into our warm-up. And so we've been given an exponential function and we've been asked to write the equation of that. And so first thing we want to pay attention to is the fact that this is a base E exponential function, and so we should be aware, of course, that the parent function y equals e to the power of x is going to be an exponential growth function and is going to have the anchor point at x equals 0, y equals 1, and so that's going to allow us in comparison to our given graph to be able to identify any reflections as well as any dilations, and then the second part of the process will be to take into account any shifts or translations. Okay, and so first of all we can see from the shape of the graph that in this particular case we've now got a decreasing function, and so that suggests to us that what we're dealing with is an e to the minus x graph, and so we've changed the sign of the x, which has caused a reflection over the y-axis or the vertical axis. And so that's the first factor that we want to take into consideration. The second factor that we want to take into consideration is that our anchor point in the graph is 3 units above the horizontal asymptote, as opposed to the parent function where it's just 1 above. So e to the power of 0 producing 1, and this in this case it's producing 3, which that then tells us what our a value is. So I'm going to start off by just filling those two pieces of information in. F of x is equal to 3 e to the power of minus, and I'm going to open up a set of parentheses so that I can accurately record the horizontal translation, or take into account that we've reflected over the y-axis first and our translation is taking place afterwards. Okay, and so what I'm going to need to do is figure out what my vertical translation was, and so the horizontal asymptote ordinarily is the x-axis, or the line y equals 0. This time our horizontal asymptote is at minus 4, and so that is going to be our k value. We've shifted our horizontal asymptote 4 down, and then we also need to take into consideration ordinarily this axis is our vertical axis, and it passes through our anchor point, and that axis has been shifted a total of 5 units to the right hand side, and so I'm going to fill in the h value as 5. And so there's our f of x function for the given graph, our transformed graph. Okay, part 2 of the warm-up asks us to determine the equation of the inverse, right? Make sure you do not misunderstand this. This is not the same thing as the reciprocal. The inverse involves the interchange of the x and the y variables. And so I'm going to begin by doing exactly that. And so step number 1, and of course f of x equals is the same as saying y equals, and so I'm going to begin by saying x is equal to 3e minus y minus 5 minus 4. And so first things first, I've substituted in my y value for x and my x value for y. Technically that is the inverse, but our expectation will be that you isolate the y term, or that you get it as f to the minus 1 of x. And so we're just going to do a little bit of rearranging. I'm going to move the minus 4 to the left hand side, and then I'm going to divide through by the 3, and so I'm going to have x plus 4 divided by 3 is now equal to e to the minus y plus 5. Not a requirement that you distribute that. I'm just going to distribute that out now to deal with that. It doesn't matter if you do that now or not. I'm then going to introduce a base e logarithm to both sides. So I'm going to take ln of both sides, and the purpose of doing that, of course, is I'm using the reverse operations. I'm going to then move my minus y plus 5 out of the exponent. And so on the left-hand side, I have ln of x plus 4 over 3. On the right-hand side, minus y plus 5 multiplied by ln of e, which of course has a numerical value of 1. And so my next step then is just to move the 5 to the left-hand side and multiply through by the minus. And so y is equal to 5 minus ln x plus 4 over 3, or of course f to the minus 1 of x equals 5 minus ln of x plus 4 over 3. Okay, all right, let's move into the focus of today's lesson. And the focus of today's lessons is the laws of logarithms and their applications, specifically applications in the area of solving of exponential and logarithmic equations. Okay, so a quick review. Remember, exponents and logarithms are reverse operations of each other, much like square rooting and squaring are reverse operations. You can use logarithms to undo exponents and vice versa. Okay, and so as I explain these rules, there's going to be a connection obviously to the exponential rules because they are inverses of each other. So when we have a base b logarithm with the product of the two values, then that results in sums of the logarithms. So log bm times n is log bm plus log bn. Okay, and so our product rule, product of values, results in sum of logarithms. Similarly, a quotient results in a difference of logarithms, and so log bm minus log bn. This is our power rule, and so when we have a constant or variable multiplied by a logarithm, then that results in the value being raised to the power of that coefficient, and so that is that's our power rule. And then our inverse property. So this one will take some time, probably in class or when we are face to face, for me to show you the proof of these. But essentially here, when we have log base b and the value is b to the power of m, that simplifies as just m. And so you could think of those as reverse operations. Another way you can think of that is if I take that m and rewrite it as the coefficient, which is essentially using the power rule that we just wrote down, then log base b of the value of b produces the numerical value 1, and of course that explains to us how we get m by itself. Similarly, the reverse operation, b as the base, log b of m as the exponent, those are our kind of reverse operations, and so both of those will simplify to m. And again, a little bit of time to show you that, and so I'm going to avoid that right now, and we'll go over that at another time. Okay, and then one of the most important rules, and something that's definitely very, very important in an honors math course and beyond actually pre-calc, is going to be our change of base rule. And so log base b for the value of m can be rewritten with any base as a quotient of the value and the base. Okay, I am going to take just a moment really quickly to show you why that works, how that works. Okay, and so I'm going to do a quick proof of this. We have got log b m. What I'm going to do is equate that to x, x representing an unknown value. All right, and so if the expression log bm is equal to some unknown value x, then I'm going to convert that logarithmic expression into an exponential expression. So that's the base, that's the exponent, that's the value. And so m is equal to b to the power of x. We can then introduce, just like we did at the earlier stage up here, just like we introduced our base e logarithm to both sides, I can introduce whichever base I want to both sides of my equation. And so let's, for argument's sake, prove the base e. So I'm going to introduce ln to both sides of that expression. I'm then going to use the power rule to rewrite the x, and so I have ln of m is equal to x multiplied by ln of b, and then if I divide both sides by ln of b, I get x equal to ln of m over ln of b, which you can see back to the original log base b of m equals x, and so that means that that must equal log base b of m, and now we've managed quite quickly and easily to prove that log base b m can be rewritten as a base e logarithm with the values m and b respectively. Okay, let's turn our attention now to starting to use these properties. And so in example 1 and example 2, we're really trying to expand and simplify wherever possible, as far as possible, each of the following expressions. And essentially these are applications of our 5 log rules. And so we're going to practice expanding and condensing these expressions, with the idea being that these are skills that we're going to need and use later on in the solving of our exponential and logarithmic equations. Okay, and so I'm just going to take the first one. What we have here is base 2, and we have the product of 3 different bases, 16a and the cube root of b. And so I'm going to have log base 2 of 16 plus log base 2 of a plus log base 2 of b to the power of 1/3. And so that's to account for the fact that the cube root of b is can be written as b to the 1/3. And then in terms of our requirement to simplify, you should be able to see, we'll just try to use the space efficiently. 16 is going to be 2 to the power of 4. And so I'm going to do a little more simplifying. We're going to have 4 times log 2, which of course is just going to leave us the number 4, plus log 2a plus 1/3 log 2b. Okay, and so principles are the same for example B and example C. And so I'll just do a couple, well, maybe just one more, and I'll just show you the start of C, and then at the end of the video I'll put up the solutions for those so you can have a quick look, but I would encourage you to try those for yourself. Okay, and so in this case we've got a on top, we've got 2 bases of 27 and b squared, both of which are in the denominator, so those are going to both be negatives. So I'll start off, we have our log 3 of a minus log 3, and in the interest of saving a little bit of time, I'm going to rewrite 27 as 3 cubed and minus log 3 of b squared, and then we can simplify one step further, log 3 of a minus just the number 3. That is of course obtained by multiplying by 3, and log 3 is going to produce the numerical value 1. And lastly, minus 2 times log 3b. Okay, and this time we have base e, so ln by definition is log base e. The entire 3 terms that we have are all being square rooted, and so each of them is going to have a power of 1/2. And so I'm going to simplify that by simply putting that 1/2 at the front and then writing out my logarithms. And so ln of 2 plus ln of x cubed minus ln of e. And then within the parentheses, there's a little bit of simplifying I can do. 1 over 2 times ln of 2 plus 3 ln x minus the numerical value 1, because ln of e has the numerical value 1. Okay. Example 2 is example 1 in reverse, quite literally. And so for this one, definitely what I'm going to do is just do example 2a and leave you to try the other two and then to have a look at the solutions. Okay, and so we have all of these as log 3, and so log 3, and we have a sum and a difference, meaning we're going to have a product of values, and we're also going to have a quotient of values. And last but not least, remember that that 1/2 is going to be the exponent of the x. And so log 3, 16 multiplied by the square root of x divided by 4, because that logarithm was being subtracted. Okay, and so in this case, as it turns out, there's one small additional step, because the 4 and the 16 do in fact cancel out, and we are expecting you to simplify. And so in this case, log 3 of 4 root x is going to be our final answer. Okay, I did say I wasn't going to do the others, but I do just want to point out in example 2c specifically that the standalone number of 3, the other two terms are ln, which means log base e, and so you can rewrite the minus 3 as minus 3 multiplied by ln e, because that has a numerical value 1, and that of course then can be written as minus ln e to the power of 3, and that's how we're going to be able to give all three of those numbers the same base and condense and simplify them. Okay, so let's move to example 3. In particular, example 3 really involves a bigger focus on our inverse property, and so the reverse properties of logs and exponents. And so here we have base 5 and log 5 in the exponent. Before you can do any kind of cancelling, though, we need to take into account the coefficient of the log first. And so step number 1 is going to be to rewrite that as 5 to the power of log 5, 3 to the power of minus 2. We must do that step first before we can then cancel out, if you wish, the reverse operations of 5 to the power of log base 5. And so that's now going to leave us with 3 to the minus 2, which is, of course, 1/9. Okay, these ones are slightly more complicated, and so I'm going to go ahead, and they're a little faster, so I'm going to go ahead and simplify these two. And so in this particular case, we have got each of these terms, we can't combine the terms themselves because we have got log 2 and log base e. And so first things first, we can use the exponent rule. Ln e to the power of log 2, 3, we rewrite as log 2, 3 multiplied by ln of e, which of course has the numerical value of 1. And then we've got a couple of different options for the second part for now. So actually I'm going to cancel that. Minus log 2 of 6. We could then combine those logs because they're now both base 2 logarithms. So I'm going to say log 2 of the quotient, 3 over 6, which of course cancels to give us 1 over 2. And so we are now looking at log 2 to the minus 1, which of course when I move the minus 1 to the front leaves us just with the numerical value of minus 1. Okay, likewise part C, we're going to have the 4 as the base and log 4. Order of operations is important though, and so you cannot use the reverse property, so this, or rather the inverse property, unless it's in the required form. And so in terms of order of operations, we must first get this exponent to a single log base 4 expression before we can use the inverse or reverse operation to remove the value from the exponent. Okay, and so we're going to start by doing that. So 4 to the power of log base 4. Here I'm going to move 3 to the exponent, so that's going to be 3 squared, which is 9, and then take into account that the addition means multiplication, and so we're going to end up with 6 multiplied by 9, which of course is going to give us 54, and then I can use my reverse operations and just end up with the number 9 sixes, which is 54. Okay. All right, and so now the idea being we're going to take hopefully what we've learned or consolidated with the use of these properties and then use those in the solving of our equations. Okay, in this case what we've done is we've organized the lesson for you in such a way that we're telling you essentially what to do. So we're going to equate exponents or we're going to equate logs. For the second part, we're rewriting as an exponent, and for the third part, factoring, and finally, for the fourth part, logs of both sides or combining. And so obviously on a quiz or a test, we're not going to tell you how to do it, but you should be familiar with all of the different possible approaches. Okay, so in this case, we're going to focus on equating exponents, which essentially means we want to get those bases to be the same. So square root of 27 can, of course, be rewritten as 3 to the power of 3 over 2. So the 3 cubed accounts for the 27. The exponent being divided by 2 accounts for the square root. Also being raised to the power of x plus 1 is equal to 3 to the power of x minus 3. And then we are able to say that since the two sides of the equation are equal in value and have the same base, our conclusion must be that the exponents are equal. And so that allows us to say 3 over 2 times x plus 1 is equal to x minus 3, which at this point is a relatively straightforward linear equation for us to go ahead and solve. Okay, and so I'm going to leave it there. Again, I'll scroll through worked solutions afterwards for you to be able to check the final answer, but I really want to focus on the key skills that you should have and not spend too much time solving linear equations. Okay, so we move to the second equation. What we have here is all of the terms with base e. What we need to be able to do is combine those logarithms before we are able to equate their values. Okay, so step 1, I'm going to move that 2 to the exponent, and simultaneously I'm going to write that as a quotient. And so I'm now going to have ln of x squared, and that is going to be divided by x minus 1/2, and that's going to equal ln of 2. I can now use the same logic. I have 2 base e logarithms equal to each other, and therefore I can conclude that the values of those for each of those logarithms must be the same. So x squared over x minus 1/2 is equal to 2. Cross multiply, x squared is going to be 2x minus 1. Rearrange by equating to 0. We will then factor in order to get our solution. In this case, x minus 1 all squared, and therefore we get our solution of x is equal to 1. Just make sure when we get that answer that we want to check for extraneous solutions, namely when we substitute that back into the original equation, does it produce any issues for us, like a base e logarithm with a value of 0 or a base e logarithm with a negative value? And in this case, it does not. Okay, second set of equations, and so in this particular case, we are going to rewrite as an exponent or rewrite as a logarithm. And essentially what this means is what we're going to do is introduce a log to solve, or we are going to convert from logarithmic back to exponential form in order to solve the equations. Okay, so our variable here is in the exponent, and so that's what we're essentially trying to isolate. And so first things first, I'll move the other two terms to the other side. So add the 3 and divide by 2, and so 75 over 2. And then to get that exponent out, to get that variable out of the exponent, what I want to do in this case is introduce a base E logarithm. That's the most logical to introduce, because combined with my power rule, I'm going to get x plus 10 multiplied by ln of e, which of course is the number 1. And so by using a base E logarithm, I make the process after the fact a little bit easier. Technically, theoretically, you could have used any base, of course, but it doesn't really make sense to use a different base than the one that I did. And so final answer, x is equal to ln of 75 over 2 minus 10 to isolate the x. Okay, in part B, I'm just going to switch up colors here. In part B, essentially, if you think of it as in this equation has logarithms, and in order to solve a logarithmic equation, you pretty much want to get rid of the logarithms. And so my first step is to take into account that I've got the sum of two base E logarithms. And so I'm going to be able to rewrite that as the product of those two values. And now I can convert from logarithmic to exponential form. And so 5x is going to equal e to the power of 2. And that, of course, is because ln of 5x is, of course, log base e of 5x. And so that's where the e came from. And last but not least, divide through by 5. Okay, next question is a trinomial with a very small disguise. And so in this particular case, we've got e to the x in the denominator on the right-hand side. It'll present more obviously as a trinomial if I multiply the entire equation by the LCD, the lowest common denominator, which is e to the x. And then I'm going to get 2e to the 2x. Remember, when multiplying, write down the base and add the exponents. And so that's where e to the 2x comes. Minus 5e to the x equals just 12, because on the right-hand side they're going to cancel. 2e to the 2x minus 5e to the x minus 12 equals 0. And this is the point at which we can go directly to factoring. For those of you who have a harder time of seeing this, just pay attention to the fact that we've got descending order of exponents, power of 2, power of 1, power of 0. And so that should help you to be able to connect to the fact that this is in fact a trinomial. If it is of use to you, you can also make a substitution like this. Y is equal to e to the x. And so that would allow us to write the equation as 2y squared minus 5y minus 12. And sometimes for students that presents a little bit easier. It's easier for them to make the connection between our equation and a trinomial, specifically a factorable trinomial. So I'm going to move that over there and just factor as is. And so the factors of 2e to the 2x are going to be 2e to the x and e to the x. And I'm then looking for the combination of factors that is going to allow me to have a difference of minus 5 and a product of minus 12. And so that's going to be a plus 3 and a minus 4. And so minus 8e to the x plus 3 is going to give us our minus 5. And so I'm now going to have e to the x equals minus 3 over 2, which of course is extraneous. The e to the x function is asymptotic at y equals 0, the x-axis, and so it'll never pass underneath. And over here we have e to the x is equal to 4, and to solve that I'm going to introduce a base e logarithm to both sides, and final answer x equals ln of 4, and the other part is of course extraneous. Okay, last one of the equations, and then we've got one quick word problem. And so in this equation, I'm going to show you a couple of different ways of doing it. And so the two different ways of doing it in this case are going to be taking logs of both sides, and then I'll show you a method that you're probably a little less familiar with, which is just combining the exponents, which is slightly faster. Okay, and so here is option number 1. Okay, and so in this case, you can introduce whatever base logarithm you want. In this case, the issue that we have is that the bases of our exponential expressions are different. And so no matter what you choose, there's going to be a little bit of additional work after that. So I'm going to choose, for no particular reason, ln. It doesn't matter which base logarithm you choose. Okay, so I'm going to take ln of both sides. All right, and the next step is going to be to use the power property. And so x minus 2 multiplied by ln of 4 is equal to x plus 4 multiplied by ln of 3. It's really important that you use those parentheses, because you have to understand that ln of 3 is just a number, an irrational number, but just a number. And so when you remove that x minus 2 and the x plus 4 from the exponent, they're actually having the number ln 3 and ln 4 distributed to them. Okay, and so I'm going to do a little bit of distribution. X multiplied by ln of 4 minus 2 ln of 4 is equal to x ln 3 plus 4 ln 3. And essentially now what I'm trying to do is isolate the x's. And so I'm going to do a little bit of rearranging. X ln 4 minus x ln 3. And I'm going to move this term to the right-hand side. So 4 ln 3 plus 2 ln 4. I'm then going to factor out my x, leaving me with ln 4 minus ln 3 in the parentheses, 4 ln 3 plus 2 ln 4 on the right-hand side. And last but not least, divide through by the coefficient of x. And there we have our final answer for x. Fairly long, fairly complicated process. And so what I want to do now is show you option 2. So I'm just going to mark this off so we don't mix the two of them up. And so option 2, a little bit faster. Okay, so here's an alternative. What we're going to do in this particular case is I'm going to start off by rewriting 4 to the power of x minus 2 as 4 to the power of x multiplied by 4 to the power of minus 2. And on the right hand side, 3 to the power of x multiplied by 3 to the power of 4. Okay, and so I'm just undoing the exponential property of when multiplying, write down the base and add the powers, or in this case adding a negative, subtract the powers. You could of course put that straight down into the denominator with 4 to the power of 2, and so it's entirely up to you if it helps you to see it. So let me do that. Oops, all right. What I meant to do was just move that over, and so that's going to be 4 to the power of 2. And then what I'm going to do is I'm going to divide both sides by 3 to the x, and I'm going to cross multiply or multiply both sides. So I'm going to take that 4 to the power of 2 to that side, and I'm going to take the 3 to the power of x to the other side by dividing. And so I'm going to have 4 to the x divided by 3 to the x equals 4 to the 2 times 3 to the 4. And I'm probably showing you a few more steps than we need, just because if you're not familiar with this, it might not be that obvious. The term on the left-hand side, this term over here, could actually be simplified to 4/3 all to the power of x. And therein lies the key step, because what I'm going to introduce now to both sides of that equation is a base 4/3 logarithm. And so now I'm going to take log of 4/3 of 4 over 3 to the power of x equals log of 4/3 of 4 squared times 3 to the power of 4. And actually, we already have our solution. Once the x moves over there, and we realize that the numerical value of that is 1, we have our final answer, log base 4/3 of 4 squared times 3 to the 4th, a lot quicker than option 1. Okay, last one. And so this is going to be a modeling problem. And so in this case, this is most likely to appear on the calculator section unless we were to ask you to produce a solution which is an exact solution. And so in this case, I'm going to treat it as if that is the case, and then I'll just show you the calculator answer as well. All right. In this case, we've got a colony of fleas, and so what we, of course, know is that things that occur naturally don't grow with monthly or daily or quarterly compounding. They grow exponentially and continuously, and so that really just means that what we're interested in is using the so-called PERT formula, P times e to the power of RT, which is the form of the equation which allows us to account for continuous compounding. Okay, and so at first inspection, which essentially means at time 0, there are 40 fleas, and so that has essentially given us the value of P, the principal or initial amount. And of course, you can see that if we were to make a substitution, A of 0 equals 40 times e to the power of 0 times r. That, of course, produces the numerical value of 1. P times that equals 40, and of course that allows us to know that P is equal to 40. And then we are given a second set of information that there are 60 fleas after 1 day, and so that's going to allow us to be able to find our interest rate. And so the unknowns here are going to be what is the percentage rate at which they're growing, and what is the initial number, and then of course t is going to be our variable. So number of fleas will vary with time. And so in this case, we know that after 1 day, so A of 1 is equal to 60, and that's going to be 40 multiplied by e to the power of 1 for time, and r for the unknown rate of growth for our fleas. And so now I'm going to solve for r, divide through by the 40, which is going to give us 60 over 40, which is 3 over 2. And I'm going to introduce base e logarithm to both sides, and so let me just move that over. Ln e to the power of r, which of course simplifies to r. And so here we have our r value, which is ln of 1.5. And now we can answer the question, how many fleas will there be after 5 days? And so that's going to be 40 multiplied by e to the power of 5 times ln of, and this time I'm going to write it as 1.5. And so we're now going to try, of course you could just type that straight into the calculator. I'm just going to do a little bit of simplifying just to show you that actually that works out rather nicely. And so 40 e to the power of ln 1.5 to the power of 5, those are our reverse operations, and so we end up with 40 multiplied by 3 over 2 to the power of 5, and so we can figure that out. So we've got 40 multiplied, that's going to be 32. 3 to the power of 5 is going to be 243, oops, all right, I believe. And then we can do a little bit of simplifying. Those two are going to cancel. That goes 4, that goes 5. Final answer, 1,215 over 4. fleas. So don't forget your unit, and do not truncate. And there's our exact answer. Okay, and then last question. If no treatment is offered to the cat, how long will it take until there are 1,000 fleas? Again, you could, the algebra setup for this is, of course, that our amount is 1,000. We know that the initial is 40, e to the power of t multiplied by ln of 1.5, which is our growth rate, or rather our percentage growth per unit of time, which is days, and then we could solve for t. The easiest way, of course, would be to solve this graphically, and so what we would do is expect you to plot this on your calculator. I would recommend plotting 1,000, then plotting the other side, and what we're looking to do is find the point of intersection. And again, in the interest of time, when you're going to go ahead and solve the point of intersection, your answer is going to be 7.939, and I'm rounding that correct to 3 decimal places. And so 7.939 days is how long it's going to take until there are 1,000 fleas.